third session handled by Dr. Naimish Zaveri from AICTE Institute of Engineering and Technology, Surat. He is PhD in Electrical Engineering from SNPIT Surat, and he will deliver about control strategy of hybrid electrical vehicle and harmonics, control of harmonics. Okay. Thank you, sir.
बिल्कुल बुके फोटो बुके ना फोटो
सिंगल फेज पावर विषय સાંભળું છે ને વોલ્ટેજ ની વાત કરીએ
लॉन्ग प्रेस
તો સિંગલ ફેઝ પાવર માં આપણે વોલ્ટેજ સાયકલ લઈએ Vm sin omega t Im sin omega t minus 5 અને પાવર કેલ્ક્યુલેટ કરીએ if you calculate power so it will be in terms of P of t 1 minus cos 2 omega t and 2 sin omega t. So that indicates average value of Vi cos phi and oscillating component twice the frequency. So one is called active power and other is called reactive power. Active power is a unidirectional component. It gives power flow from source to load, and reactive power is which component? Imaginary component. So what happens to reactive power? થોડુંક ઇન્ટરેક્ટિવ બનાવો તો જરા મજા આવશે એમ.
It is continuously rotating between source and load. It is available.
હા, it is exchange between source and load. બરાબર? This is the characteristics of reactive power. This is simple impedance diagram. Real component R, X, Z. If you take IR, IX and IZ, then impedance triangle converts to voltage triangle. Multiplying again I, voltage with I, this will convert into power triangle. So it is I square R, I square X, I square Z. So apparent power comes out to be active component plus reactive component, and S equal to Vi conjugate. So what is Vi conjugate?
It is for lagging current.
Either lagging or leading. We simply mention Vi conjugate. So
Conjugate is for to give that P plus JQ.
What?
Otherwise, if you do not give that conjugate, it will come as P minus JQ.
no, no.
Is P plus or minus JQ.
It has nothing to do with P minus JQ, P plus JQ. Why we mention conjugate here? So simple. This is your voltage phasor. This is your current phasor. Suppose voltage phasor is making angle with reference to reference is theta 1, and current phasor prepares angle theta 2. So if you mention simply V into I, this will turns out to be voltage magnitude, current magnitude at an angle theta 1 plus theta 2. Whereas power factor definition is, at the first slide we have seen P equal to VI cos phi and Q equal to VI sin phi. So phi is naturally comes because it is angle difference between voltage phasor and current phasor. conjugate, it's a V into I at an angle theta 1 minus theta 2, which is a correct definition of phi. Getting my point? पड़ा से cover? So to obtain this, we are making VI conjugate because it is VI cos phi. Angle difference we have to take. Right? Now बराबर है? Okay. So this is impedance triangle and this is power triangle. Further. These are some basics. I am discussing basic things. But hope you will get something. Acha. Linear load. So, what type of load is linear load? Resistive only. Other? Induction motor is linear load. Induction motor.
Question.
Which are the resistive load? Sorry, which are linear load?
Whatever the terminal voltage available across it, exactly the same pattern will follow the whatever the current that is carried.
Current.
That is linear.
Current follows the same pattern as a voltage. Barabar. So that's a linear. Linear relation exhibits. Right? So R, X, XL, XC, they all are linear. Right? Okay. Next. Non-linear load. Non-linear load means
The current taken
Current doesn't exhibit-
doesn't take the
okay.
Profile
So
of
which type of load is linear load?
which type of load is linear load. RLC is a linear load.
Huh?
RLC is a linear load.
RLC is a linear load, non-linear load.
Rectifier after converting DC at the output side of rectifier and the current that is drawn by the input side of the rectifier, it will not follow the pattern of the voltage.
So it is non-linear load.
Non-linear.
Barabar? So non-linearity exists right from diode.
Yes.
If you take power electronics, if you start power electronics working, so semiconductor devices starts with the non-linearity, right? So any kind of power electronic circuit, whether you use converter, drive, arc furnace, everything is non-linear because in that current doesn't have a linear relation with the voltage. So it is called non-linear load. Next. So these all are non-linear loads. Single phase rectifier. If you see the pattern of source current, single phase rectifier, if you see the pattern of source current, it will be a single pulse per cycle.
Yes.
Barabar? And if you take three phase, it will be a
Three. Two cycles.
rectification is DC. But what happens to AC? See, if you take rectifier, three phase rectifier, this side you will get DC. But what about if you measure current from here with current sensing? What will be the current spectra approximately? Power quality and effects कोई बनावे છે? Okay. See, if you measure a current here, there will be a double hum per cycle. See, if there is a single phase rectification process, there is a single hum per cycle. So, this is a voltage cycle, this is a current cycle. If you see three phase rectifier, double humps per cycle. This is a normally pattern. Depends on other parameters. R, L, C. Rectification is same. Right? So both have a different phenomena, characteristics we will see later. But these all are here. Here you can see this is a double hump. So it is converter or rectifier. SCR as a converter or rectifier if you use, then there will be a double hump per cycle. It's a general tendency. You have to keep in mind. Okay, this is a tendency. Barabar? Okay. So three-phase rectifier, its output waveform. Fan regulator, it is also one kind of non-linearity. Fan regulator માં શું આવે? कोई आइडिया?
कैपेसिटर भी है
આઈસ્ટર મોસ્ફેટ એવું તો ના આવે, પણ એક કમ્પોનન્ટ તમને કહું. ટ્રાયોકાર બરાબર, આ એસી છે, આ ફેન છે, this is RC circuit બરાબર, આ R, this is diode અને આ triode. So normally 4 to 5 components are there in fan regulator: diode, triode, fixed resistor, variable resistor and capacitor. What is the nature of output of fan regulator? भाई बराबर છે फ्लो? हाँ? What is the output of fan regulator? Variable voltage. It is RMS voltage or average voltage? RMS voltage or average voltage? Average કહેશો તો 0 થઈ જાય. AC ની કોઈ પણ સાયકલ average is 0. We are specially defining in terms of RMS. So whenever there is output of fan regulator, you have to call that voltage RMS voltage only. बराबर? Whether it's a 20 volt, 40 volt, 48, 230, it's RMS voltage. बराबर? It's not average voltage. तो आपका 11 kV અને 33 kV આવે એ કયા વોલ્ટેજ આવે? ટ્રાન્સમિશન લાઇનમાં
Line to line.
RMS. Line to line
RMS.
RMS. So speak like that. It is line to line RMS voltage. बराबर? Okay. Next. So these are non-linear load. Few patterns are shown. Single phase current. Any devices operating in non-linear mode, they are non-linear. See. Now one term introduces, that is harmonics. बराबर? So what is harmonics? Integral multiple of fundamental frequency is harmonics. And a non-integer multiple હોય તો non-integer multiple fundamental frequency હોય તો શું કહેવાય?
Internal.
Interharmonics.
Internal.
Interharmonics. And an integer multiple of fundamental frequency is called harmonics. Next. अच्छा. So this is a way of defining harmonics. Again, આગળ કરો. There are two way of defining harmonics. આગળ. જો. I have got one wave which is completely distorted. It is no more sinusoid. So how to get its frequency information? That there is a fifth harmonic, seventh harmonic, eighth harmonic, 10th harmonic.
FFT.
FFT. बराबर? FFT which decomposes
Into different
this
frequency.
into the various frequency spectra, so that you can come to know that this harmonic content is there in the waveform. बराबर? Next. waveform, one periodic waveform is given. This is fundamental frequency, and these all are the frequency which is harmonics, right? So all harmonics together. Now second question, very important. Normally we are analyzing odd harmonics, like third harmonic in system, fifth harmonic in system. Why not fourth harmonic in system, sixth harmonic in system?
Symmetry.
Huh?
Half wave symmetry.
Half wave symmetry. खबर पड़ा सर? Half wave symmetry. So normally we call these as only odd harmonics, right? Okay, next. Harmonics can define in two ways. One by the order and one by the sequence component. Say if you take simple order, then these are the harmonics. 5th, 7th, 11th, 13th, 17th. They are number itself. So odd number itself. So they are called odd harmonics. When 2, 4, 6, 8, they are number even. So they are called even harmonics. And third category comes, that is
Multiple.
three-plane harmonics, right? Third, ninth, fifth, it is multiple of 3. What is the use of it? Triplet harmonics क्या जो है आपने? अरे केवी दिखता है आपने? बोलो नहीं.
आवे के नहीं आवे
आवे के नहीं आवे पहला बोल.
इफेक्ट ना है ट्रिपल हार्मोनी
है नहीं इफेक्ट होता है. वो मेजर इफेक्ट है.
એની સૌથી વધારે
સૌથી વધારે ઇફેક્ટ થાય. આના પછીની સ્લાઇડ બતાવીશ. ચાલો કઈ નહીં. Keep in mind there is third type of harmonics which are triplet harmonics, right? But that we will see later. This is harmonic order. So I have defined one notation: 3k plus 1, 3k plus 2, and 3k plus 3. K equal to 0 stands for positive sequence harmonics, right? So here if you take k equal to 0, it will become first. Second time k equal to 1, it will become 4. Third time k equal to 2, it will become 7. So these all are called positive sequence harmonics. There is a significance why we are defining in this way. Then negative sequence, again k equal to 0, 3k plus 2. Then second harmonic, fifth harmonic, 8th harmonic, 11th harmonic, they are called negative sequence harmonic. And these are zero sequence harmonic. So what is the use of this positive sequence, negative sequence?
The
ये
two
क्या बोल
are
रहा है?
not ideal component for the load, negative and 0.
हाँ ये बराबर है, not ideal component, even not positive.
Yes.
बराबर. If you talk about 4th, 7th, are they positive? No. So positive sequence added with the fundamental component and producing magnetic field which demagnetize the original field, right? As it is in line with the positive sequence. So negative sequence, they are ultimately demagnetize the field. So suppose one motor is working, induction motor, and that all positive negative sequence harmonics appear, then positive sequence will help in demagnetization, negative sequence will help in cross magnetization. It will try to distort the magnetic field, right? Whereas positive sequence, they are in line, so they try to demagnetize the original field. So that is a use, right? Next, so by this way you can have a order of a magnitude, order of a harmonics and sequence component of the harmonics, right? Okay. Positive sequence, negative sequence, zero sequence, right? As you all aware, see here, very important thing is discussed. Triplet harmonics. Triplet harmonics, when it appears in triplet harmonics, its overall time period, this is one cycle time period is 360 degree, right? Whereas if you talk triplet harmonics, it is 150 hertz frequency. अभी मैंने cycle, second cycle and third cycle, right? So you can see here phase A third harmonic 3 cycle, phase B third harmonic second cycle, phase C third harmonic first cycle. So one particular point, this all will come in single point. So if your neutral system is available, so this all three become additive and neutral current harmonics will become higher. So normally neutral current wire we design half size. So if there is a 1/3 of third harmonic, right, and there is a 8 ampere of a neutral is designed, and third harmonics is 3 ampere, so all three phase R by B become 9 ampere, and so it will give a fusing of neutral wire. So burning issue of neutral wire happens in many apartment, right? So neutral point will become float, right? અને એ જ કારણથી
વોલ્ટેજ અનબેલેન્સ.
હા વોલ્ટેજ બધા અનબેલેન્સ થઈ જાય છે, રાઈટ? નેક્સ્ટ સોર્સિસ ઓફ હાર્મોનિક કરો ને બીજું કયા કયા સોર્સિસ ઓફ હાર્મોનિક છે? નેક્સ્ટ ટ્રાન્સફોર્મર. ટ્રાન્સફોર્મર તો આપણે જો લિનિયર લોડ છે, સો વાય ઇટ બીકમ્સ સોર્સ ઓફ હાર્મોનિક્સ?
મેગ્નેટાઇઝિંગ સ્ટાર્ટિંગ ઇન્ડસ્ટ્રીયલ.
હા, ઇન્ડસ્ટ મેગ્નેટાઇઝેશન બેવ. So transformer at maximum saturation region, it will act as a non-linear load, right, and produces a harmonics, right? Second, generator and motor. Generator and motor in normal condition are linear load, right? But in certain condition like generator માં જો એની shaft through નહીં હોય, બરાબર, તો generator કેવી રીતે ફરે? શાફ્ટ થ્રુ નહીં હોય તો અનબેલેન્સ વોલ્ટેજ આવે. કેડી અને કેપી બરાબર નહીં હોય. કેડી ઇઝ ડિસ્ટ્રીબ્યુશન ફેક્ટર, કેપી ઇઝ પીચ ફેક્ટર, બરાબર? જો એમાં થોડો અમથો પણ ફેર હોય તો નોન લિનિયરિટી પ્રોડ્યુસ થવાની પોસિબિલિટી છે. થર્ડ, ફિલ્ડ એક્સાઇટેશન. જનરેટરનું ફિલ્ડ એક્સાઇટેશન ઇઝ નોટ પ્રોપર. સો ધીસ ઓલ થ્રી રીઝન મેક જનરેટર non linear. Otherwise in simple case it is a linear, બરાબર? એટલે ડિફરન્સ આપણને ખબર હોવો જોઈએ, કારણ કે મોટર જનરેટર બધા ઇલેક્ટ્રિકલ ઇક્વિપમેન્ટ they are linear load unless and until there is a power electronics incorporated, બરાબર? Okay, then very heavy load is arc furnace and arc welding. Arc furnace heavy process, refining, tuning, filtering, and every time number of harmonics पैदा થાય, બરાબર? and they all are non-linear. As harmonics term comes into picture, the non-linearity starts, right? Yes. Switchboard power supply. Next, and very important is variable frequency drive. A switchboard power supply क्या वपराય? Where we are using SNPS? Everywhere. તમારા લેપટોપ સાથે જોડો છો તો SNPS છે. તમારા લાઈટ સાથે અત્યારે આની લાઈટ તો કન્વેન્શન છે, LED છે કે નહીં? જ્યાં જ્યાં LED આવી ગઈ ત્યાં બધે ડ્રાઈવર યુઝ થાય છે, and that all driver are called SNPS.
અનરેગ્યુલેટેડ રેગ્યુલેટેડ.
હા, બરાબર? So it's a heavy source of harmonics, right? SNPS, and as per EPI report, nowadays maximum number of SNPS અને વપરાય છે VFD. એક બાજુ એનર્જી સેવિંગ કરીએ છે, બીજી બાજુ આપણે VFD યુઝ કરીએ છે. VFD also is heavy non-linear load, right? Why heavy non-linear load? VFD માં શું આવે?
સ્વિચીસ, બ્રિજીસ.
Bridges, બરાબર? It converts 3 phase to DC, DC to 3 phase AC. So heavy non-linearity occurs, right? Next, converter and cycloconverter. Yes, major player in harmonics generation is VFD. કરો?
Yes, correct.
તમે જોયું છે આ VFD છે
VFD.
અને એની સાથેની મોટર છે. તમે જ્યારે જ્યારે VFD into the system is prone to produce harmonics, right? Harmonic system માં આવવાના છે, right? Next, all residential area. Next, acha, so main component of defining harmonics is THD, as we all aware, barabar. It is called total harmonic distortion. But before that, let us see what is THC. It is total harmonic current. So harmonic current is all other than one. One is a fundamental frequency, 50 Hz. Other than one, all are harmonics. So this is n raised to 2 to 40. 40 is a number taken in USA. US and Europe, they used to measure harmonics up to 40 only. As they said, above 40, it is not going to affect the system. બરાબર? જો તમારો AC wave છે 50 Hz, ત્યાં આગળ 60 Hz હશે, and if there is a harmonics above 40 or 45 range, so it is not going to affect much to its sinusoidal wave, right? So normally it is taken as THC, and THD is total harmonic distortion. It is calculated on the basis of fundamental current. બરાબર? THC upon fundamental current, it is going to be a THD, and this is total demand distortion. It is most widely used notion in USA, North USA. બરાબર? It is total demand distortion. બરાબર? So there is a difference. This is calculated on the basis of fundamental current.
Yes.
બરાબર? If you take a one particular spectra of a current, it may contain 50 ampere, 20 ampere, 16 ampere, third, fifth, seventh, ninth harmonics. If you add up, it will become 80 ampere, right? So total load current will become 80 ampere, whereas fundamental current is become 50 ampere. Right? So TDD is based on total load current,
Demand.
and THD is based on
Fundamental component.
So only keep in mind, right? These are important notion. Effect of harmonics, yes. Next, are you comfortable with my flow? Slow junction. Different harmonics current are producing extra heat. Acha. All harmonics, they have a general tendency to heat up the equipment, right? Whether it is motor, whether it is generator, whether it is transformer, this is one natural phenomena. એટલે one thing is that it creates a heat. Second thing, skin effect produces. Skin effect is what? Huh?
Current will try to take path other than its central uniformity.
Current has a tendency to flow on outer surface only. બરાબર? કારણ કે વચ્ચેનો જે reactance છે તે heavy હોય. બરાબર? તો XL is what?
Inductive reactance.
Any definition?
Opposition by that.
2 pi FL.
2 pi.
So that it contains a frequency component, right? So when frequency increases, suppose 7th harmonic increases, so this will become 2 pi f7l. So naturally inductive reactance will become dominant, right? એટલે maximum portion એ cover કરવા try કરશે, right? So current has a less chance that surface પર પણ એને જગ્યા નથી મળતી, because it is occupied right from center to surface. એટલે inductance એટલો બધો વધી જાય કે કંડક્ટરના સરફેસ પર કરંટને એકદમ જગ્યા મળે. તો હવે આટલો કંડક્ટર યુઝ શું કા કરવો? વચ્ચેનો કંડક્ટર કાઢી નાખીએ અને હોલો કંડક્ટર યુઝ કરીએ. કેન બી?
हाई फ्रीक्वेंसी में करते हैं.
નહીં, મિકેનિકલ અરેન્જમેન્ટમાં પ્રોબ્લેમ થાય ને, એમ પાઇપ જેવો કંડક્ટર યુઝ ના કરી શકીએ એટલા માટે. બરાબર? તો નેક્સ્ટ, ન્યુસન્સ ટ્રિપિંગ ઓફ સર્કિટ બ્રેકર. અચ્છા, these are all effects of harmonics. Noisy operation થાય, damage to sensitive electronic equipment, zero crossing noise, maximum value of supply voltage, digital, number of problems. One major problem is power factor.
actually it's a fundamental component of difference between voltage and current. But due to harmonics, it's also at different angle. Means the distortion is also there and displacement is also there. So it will not at all that now only fundamental component of current.
Distortion and displacement both together, બરાબર? દાખલા તરીકે બેઉ 60% છે, so one is 60%, other is 60%, તો 6 ને 6 36, 0.36%, so power factor deteriorates more.
Yes.
બરાબર? તો next આ main diagram છે. All of you must be aware with this. This is called power tetrahedron. બરાબર? You might have come across this term first time, I think. પહેલી વાર તમે બધા આને સાંભળો છો. પાવર ટ્રાયંગલ ની ઉપર એક સ્ટ્રક્ચર આપણને મળે છે, that is called power tetrahedron. What exactly it is? So as we are aware that in case of power factor or a power triangle, simple active component, reactive component અને એમાંથી આપણે પેલો કાઢી લીધો તે. So this is power triangle. Power triangle is made up of active power, reactive power and apparent power. So what is this? Power tetrahedron. ये શું છે એ સમજી લો. This D is one more phasor added and D stands for distortion. So all harmonic power means V2 into I2, V2 into I3, I2 into V3, I2 into V4. Right? Other than fundamental V1 and I1, any સિવાયના all combinations, they are taken as a distortion or harmonic power. So these you take as a reference. This is third component. Like if you take this as a active power and this as reactive power, so if I am standing here, the vector pointing from this corner to my head is distortion factor plus displacement factor, right? Because the term distortion appears in a picture and that is taken as a gamma. ये નથી લખ્યું gamma, right? So if in my system there is no distortion, that means that this vector is on the ground. Getting? So distortion is going to diminish. હું જો અહીંયા બેસી જાઉં, બરાબર, તો એ આખું distortion 0 થઈ જાય. So gamma component is cos gamma, which is responsible for distortion, right? So cos 0, that's a 1. So cos gamma is 1 and distortion is removed. Then remaining component is only power triangle,
SPQ.
right? And that's PQ. Okay, next. These are all other power quality issues: temporary interruption, long-term interruption, momentary interruption. So there are many power quality problems, right? This is all voltage sag. Sometimes it happens, voltage sag in the picture, right? When there is a flicker, dimming light, excessive light, so they all are power quality problem. Sag is also under that category. Swell is a rise of voltage, that is also under that category. And a transient and spike, you might have come across this phenomena, transient, right? So that will also some kind of power quality problem. Next. તમે લોકો કોઈ પ્રશ્ન પૂછવો હોય તો પૂછી શકો છો. હું જાણતો હોઈશ તો બતાવીશ, નહીં તો હાથ ઊંચા કરી દઈશ. This is notch, this is noise. Communication frequency are added in power frequency, so noise will happen. This is notch. Every certain interval, this notch phenomena will appear in case of inverter. when one switch is commutated and one switch is on. Barabar. So in that case these notches are appearing. And finally harmonic distortion. Right? Next. This power quality अच्छा एक प्रॉब्लम एवो ऊभो थयो કે utility is responsible for maintaining quality of voltage waveform or customer is responsible for limiting harmonic currents injected into the power system. So दाखला तरीके there is a one system, right? Source and there is a load, and if you measure harmonics, the system ma harmonics appear kiya, so who is responsible?
Consumer.
Consumer. So what steps to be taken by the consumer?
Power factor improvement devices at the load side.
What step to be taken by consumer? So utility system, they restrict certain limit कि भाई your THD of current exceed 5% of the rating, then you will be penalized. तो તમને penalty થશે 5% ની ઉપર જો તમે THD રાખ્યા તો. અને same way under 69 kV voltage harmonic should not exceed 3%. Barabar? If you cross this limit of 5% and 3%, then you will be penalized. Barabar? So it is a responsibility of the regulatory committee because they have defined the norm, as well customer. Next, these are some standards of IEEE in which you can have a harmonics at number of places, electrical utility reliability, all indices. One more is missing, IEEE 519. Next, so these are the standard norms. Below 69 kV, 3% of the voltage THD, and current THD is 5%, right? Next, these are some actual survey we have taken at our premises. Barabar? So laser machine THD current comes out to be 36.19% and THD voltage comes out to be 2.4%. Why it is so? If you see current THD, it is more and voltage THD is less. So basically अराजकता कौन फैलावे છે, કરંટ કે વોલ્ટેજ?
Current.
કરંટ. તો વોલ્ટેજ નો શું રોલ?
To force the current.
See, there is a source, there is a load. If you take a non-linear load, it draws a non-linear load current. Though, if you measure the voltage, then there is a voltage distortion. So, current is a non-linear and it makes IZ drop.
It's a non-linear.
That's non-linear. So, IZ drop that creates a voltage, voltage distortion, right? So, if you see from source to load, so there is a maximum voltage distortion at load side and source side normally more or less clean. Barabar? As you go on approaching load, it will be a more, right? Next, embroidery machine. In that also we have taken THD current 70.4, THD voltage 0%. Next, આ થોડા ઓબ્ઝર્વેશન મે લીધા છે THD current અને THD voltage ના. Next, water jet looms, the load which are available in Surat or industries around Surat. બરાબર? ત્યાં અમે જાતે જઈને torrent power ના યોકોગાવા instrument થી we have taken a measurement. So current and voltage measurement we have taken. Why? You see, this is a voltage spectra and this is a current spectra.
Rectifier.
લેપટોપમાં કેમ વધારે આવે SNPS બરાબર DC રેગ્યુલેટર તમે વાપરો છો 230 વોલ્ટમાં પ્લગ ઇન કરો છો અને વોલ્ટેજ એને જોઈએ છે 5 વોલ્ટ 12 વોલ્ટ 1.0 એમ્પિયર એ ક્યાંથી લાવવાના તો that uses SNPS SNPS a heavy non-linear load છે so that creates a TSD current બરાબર next માઇક્રોવેવ ઓવન બધા રીડિંગ લઈ લીધા છે next fan regulator you see fan regulator also while operating fan regulator it creates heavy non-linearity right because the sinusoidal waveform is not maintained problem ક્યારે જ આવે આપણને બધાને ખાવા માટે શું જોઈએ દાળ ભાત શાક ને રોટલી બરાબર as you keep on adding Chinese every day what will happen to your body right so Chinese simply act as a harmonics બરાબર એક બે વાર ખાઓ તો ચાલી જાય એમ સિસ્ટમમાં આવી જાય તો એ સબસાઇડ થઈ જાય but as you keep on daily eating Chinese so what will happen your body will deteriorate right so સિસ્ટમમાં harmonics desirable નથી right okay next arc furnace is heavy load right અને severe harmonics પેદા કરે right next adjustable speed drive જો મેં તમને કીધું એ પ્રમાણે કે when you use adjustable speed drive so ultimately it is a rectifier DC bus and inverter right so naturally it is going to produce 2 ohms per cycle huh? these are having variety depends on L and C right so as it is shown THD voltage is ranging from 0 to 4% whereas THD current is ranging from 3-5% to something 131% right so current is a major source of harmonics right and along with drop it makes voltage also distorted so accordingly as we have seen power factor that is also going to change right harmonic filtering technique બરાબર તો કેવી રીતે હાર્મોનિક્સ ને આવતા રોકી શકાય so one is a prevention other is a correction બરાબર so if you go for prevention બતાવો next જો prevention માં there are 3 techniques one is if you prepare a DC so LDC is a lower side chop that is good enough for removing harmony right second AC line reactor right normally we are measuring harmonics in AC side DC side पर measure થાય नहीं થાય AC side पर આપણે measure કરીએ so if you use DC ring reactor and AC line reactor so less number of harmonics come into picture right okay so this is all design and second thing is multi-pulse converter you know if you use 6 pulse converter then harmonic is different if you use 12 pulse converter harmonic is different why it is so
numbers of switching operations that
switching operation and second thing is there is a phase shift in transformer barabar if there is a delta and star so there is a phase shift right so during phase shift and overlap the angle switches to the other right and during that time the harmonic reduces right जो पहला 60 डिग्री છે દાખલા તરીકે if you are taking six phase rectifier 6 pulse rectifier right So that creates a 6 pulse DC. On AC side, you have this type of waveform. But if you use 12 pulse converter, right? So one is connected with star side, other is connected with delta side, and both are together connected with a common bus. So if you take a supply system, there harmonics is naturally reduces, right? So as you go on increasing the number of pulse per cycle, the harmonic reduces. If you go for 24 pulse, the more harmonic reduces, right? So I think that's formula. Something is 6p plus or minus 1. કંઈક આવું કંઈક છે બરાબર. નંબર ઓફ પલ્સીસ ના તો શું કહેવાય
બરાબર. Order of harmonics will be 6 and plus or minus 1.
હા
બરાબર.
ઓર્ડર ઓફ હાર્મોનિક્સ
6 and plus or minus 1. So first harmonic that will appear will be 5th and 7th. 1, 5, 7, 10, 11, 13 and so on with 6 pulse.
ના 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 મને એનું ફોર્મ્યુલા જોઈ છે.
Same sir. પેલામાં 12 and plus or minus.
અચ્છા 6n પ્લસ ઓર માઈનસ 1. ના તો પછી 2 પલ્સ કન્વર્ટર હોય તો
આમાં સર હવે 12 pulse લઈએ ને તો 12 and plus or minus 1.
ના 2 પલ્સ કન્વર્ટર માટે શું થાય બદલાઈ જાય.
2 and plus or minus 1.
If you use single pulse rectifier, it's a 2 pulse converter.
Then it is not applicable. It is applicable.
ના એ તો
for
ફોર્મ્યુલા
three
બીજી છે.
phase. This is for 6 pulse 3 phase one. This part is 6 and
હા
plus or
ના ના
minus.
એક જનરલાઇઝ ફોર્મ્યુલા એવી છે કે if you use single phase, so that is 2 pulse converter. So naturally third harmonics will going to appear. If you use 3 phase rectifier, so naturally third harmonics will be out.
So in
This-
this there will be direct 1, 5, 7 because n is equal to 1 if you keep it will be 5 and 7.
Number of pulses P.
This is correct, sir.
K P plus or minus 1. K stands for
Number
1. Number of pulse P.
Ah.
So this will be the formula. Kp plus or minus 1. K stands for 1. Number of pulses per cycle. So if you use single phase rectifier, there are 2 pulses. Right? Single phase rectification creates a 2 pulse. So 2 plus or minus 1. It is 2 into 1, 2 plus 1, 2 minus 1. First and third. Right? Then this is K equal to 1 and P equal to 6. If you use 3 pulse rectifier, sorry, 6 pulse rectifier,
Fine, sir.
if you go for 3 phase rectifier, so output will be 6 pulses on DC. Right? So here it is 6 plus or minus 1. Yes. So 5 and 7. So naturally third harmonic will be out. So the formula is I think more or less this Kp plus or minus 1. Right? So that decides the number of harmonics appearing system. So if you go for a 12 pulse and K equal to 1, so naturally 12 plus or minus 1. So 13 harmonic and 11 harmonic.
It will shift it
So
to
third, fifth, seventh
higher
will be
side.
naturally out. So there are 2 advantages. As you go on increasing the number of pulses on DC side, right?
Harmonics will
So
be
DC
shifted
is
to-
going to be a smoother,
Ah.
which we desire.
Yes.
DC is going to be a smoother. That is one advantage. And second advantage is we can control harmonics on AC side. Right? Okay. Next. Correcting solution માં આપણે શું જોઈએ? Next કરો. Passive filter. પેલું prevention હતું કે if you want to prevent the harmonic, then DC side filter, AC side filter, topology transformer ની number of pulses per cycle વધારવાના. So these three are preventing solution. Correcting solution માં if we cannot do this, still harmonics appearing system, then how you can control? Then there are 2 ways: passive filter and active filter. So passive filter normally L and C અને bank મૂકવામાં આવે and they are tuned to particular frequency.
Yes.
દાખલા તરીકે 250 Hz frequency comes into picture, then L and C tank is designed in such a way that whenever there is a 250 Hz frequency, that will provide a shortest path.
Yeah.
બરાબર? So that dumb 50 Hz component will done and system will be fifth harmonics free. But normally what happens in a system, you might have heard the word resonance, right? So there is a one word resonance and second word is detuning, right? If it is designed for 250 Hz and something other frequency comes, then that passive transformer, passive filter is detuned. So a detuning में extra problem create करे, and then there is a resonance appear. Either L અને C ની બેવની frequency match થઈ જાય, XL અને XC match થઈ જાય, તો it will create a resonance, right? અને એ voltage amplification કરી દેશે, right? So in one case current amplification, in other case voltage amplification, series and parallel. So these are the phenomena happens. So normally we don't prefer passive filter. તે છતાંય SR માં આર્સેનલ મિત્તલમાં મૂકવામાં આવ્યા છે. If you happen to visit, હવે આર્સેનલ મિત્તલ થઈ ગઈ, તો there you will find huge amount of passive filter. ત્યાં આગળ મૂકેલા છે. L અને C ની heavy tank મૂકેલી છે, which you can see. Next, very important is nowadays it is in operation active filter. Active filter are of two type: series active filter, shunt active filter. Series normally we use for voltage rectification, right? But voltage is very less in harmony, so we normally go for shunt active filter, right? Because current is a major source of harmonics, right? So when we go for a shunt fashion, so that current can be captured and less burden to the system. Series system માં burden કરે છે, જ્યારે shunt system માં burden કરતું નથી. Same rating ઉપર you can design the VA, right? If your system is 30 kVA, you can design 30 kVA line, right? So L and C design accordingly, right? Shunt. These are the classification. Number of classification are there. VSI and CSI, voltage source inverter, current source inverter. Then depends on pulse generation. There are so many: hysteresis band control, carrier base control. So either a triangular base, any one carrier is to be taken, and you have to compare the carriers. Carriers are the comparison karo, generation of pulse, and that is given, right? Then sliding mode control, which is latest. Dead bit control, neuro fuzzy logic based control, બધા પર કામ થઈ ચૂક્યું છે, right? Reference current generation. તમારે સિસ્ટમ માં હાર્મોનિક્સ આવ્યા, તો how to identify the harmonics? તો ક્યારેક તો કંઈક ગરણી જેવું કામ કરવું પડશે ને. ગરણીમાંથી ચાની ગરણીમાંથી જેમ કૂચો કાઢીએ તેવી રીતે હાર્મોનિક્સ ને કાઢવામાં આવે. દાખલા તરીકે in our system, if we take a particular spectra, right, you remove the fundamental component, rest of all are puja, right? I mean harmonics, and that harmonics is to be compensated, barabar? So you have to produce a reference NT 180 degree out of phase, right? એટલે ક્યાંય તમે કેન્સલ કરતા જાઓ, ક્યાંય ડબ કરતા જાઓ, right? So reference current generation is number of, major is frequency domain and time domain, and third is wavelength, time and frequency combined, right? Okay. એના માટે પણ different current technique છે. Instantaneous reactive power theory, sine wave subtraction, notch filtering, that is 50 Hz ને notch કરી દે, PDM freeze current control, and synchronous reference control, synchronous reference frame theory, and DQ control, right? So these are all time domain technique. In frequency domain we can go for FFT base or least square method, barabar, where we can go into the detail. Limitation with frequency domain method, this is very important. જો આ રીતે છે, this is your system, utility, non-linear load, load current, source current. As it is a non-linear, so it appears in a source side also, right? પણ થોડો ઓછો થતો જશે કરંટ. Why? Because its travel is long. So the current spectra, if you take load current or a source current, then it is this, right? So a simple example is shown how to extract fundamental component. So IS1, 1 stands for fundamental component, sin omega t minus phi 1. So that includes active and reactive. Fundamental. Rest of all are, so it is h equal to 2 to infinity. Rest of all are harmonics. So that harmonics is to be removed, right? So here source, load, you can see the waveform. Load current is non-linear, source current is sinusoidal, and you have to design an active filter which we call connected in shunt fashion, or also it is called static compensator. So it is called shunt active filter, and shunt active filter generates a reference current, and then reference current is injected. So the load current compensates, and on other side you will find only source current, right? Then there is a detailing about the reference current control theory. Next, this is instantaneous power theory. I don't know, are you aware of this or not? તમે આનાથી aware છો? છો ને? So here there is a Clark transformation, right? It converts 3 phase to 2 phase. The reason is it generates 2 phasor 90 degree, whereas in 3 phase it is 120 degree. So mathematical complexity is introduced. To reduce the mathematical complexity, we are converting 3 phase to 2 phase, both voltage and current, right? Both 2 phase voltages, 2 phase currents. So V alpha, V beta, I alpha, I beta, and multiplying it converts into active current, active power, and reactive power, right? So here it is assumption that reactive power that incorporates harmonics also. So if you take only active power, it allows. I mean, instantaneous reactive power theory is efficient up to certain extent. બરાબર, પણ જેમ એરા આગળ વધતો ગયો, નંબર ઓફ લોડ, નોન લિનિયરિટી હેવી ને હેવી અંદર ઇન્ટ્રોડ્યુસ થતી ગઈ. So there are limitation of instantaneous reactive power theory also, right? So other theory are to be developed, and so people have developed synchronous reference frame theory, right? Next, આ બહુ સરસ કોન્સેપ્ટ છે. આ જે P જનરેટ થાય છે તેમાં બે કમ્પોનન્ટ હોય, એક DC કમ્પોનન્ટ અને એક AC કમ્પોનન્ટ. DC component we call average component, AC component we call oscillating component, Q average and Q oscillating. So see, removal is up to here. If you want to remove the harmonics using instantaneous reactive power theory, then oscillating component, P oscillating component, Q average and Q oscillating. If you remove this much, then there is only fundamental component, right? પણ મેં તમને કીધું એમ કે IRP ની એક લિમિટેશન આવી, હેવી ને હેવી નોન લિનિયર લોડ ઇન્ટ્રોડ્યુસ થયા, એટલે 1980 85 90 સુધી અકાદીની instantaneous reactive power theory was very popular, but then a non-linearity introduces lot, so that theory fails up to certain extent. So people have developed synchronous reference frame theory, right? I represent generate. This is a basic block diagram. આવી રીતના ત્રણ સિગ્નલ લીધા, લોડ કરંટના ત્રણ, સોર્સ વોલ્ટેજના ત્રણ, then they have developed clear transformation,
Yes.
power calculation PQ અને power to be compensated, તો એને કાઢ્યો અને એના પરથી રેફરન્સ જનરેટ કરીને 180 ડિગ્રી ઇન્જેક્ટ કર્યો. So that is a instantaneous reactive power theory. Next, synchronous reference frame theory. This is also very important. Synchronous reference frame theory માં three phase signal are first of all converted into alpha beta. So alpha beta is a stationary reference axis, right, which converts alpha signal beta signal on 90 degree, V alpha V beta. Then with the use of path, because normally in motor there is a rotor, so naturally rotating reference signal has to be catched, right? So stationary axis to shifting to rotational axis we use DQ axis, right? So normally in all electrical machine, even in PMSM, permanent magnet synchronous motor, PMSM also we are using DQ axis, right? So with the use of path transformation we convert signal into DQ, right? And then again reverse processing acha DQ ma you will have a two component ILD ILQ. This high pass filter ની મદદથી આપણે એવરેજ કોમ્પોનન્ટ કાઢી નાખીએ છે. એવું કહેવાય છે કે all average components are responsible for harmonics and reactive power, so they are removed and only the oscillating component are used
Generating
for
reference.
injection, right? So in a simple way this is a synchronous reference method. હવે આમાં તમે કરવા જાવ તો બહુ લાંબુ થાય છે, એટલે I have explained a simple concept. બરાબર? Next, આ modified synchronous reference frame theory છે. Next, this is system configuration. તમારે કોઈને સિમ્યુલેશન કરવું હોય તો you can directly take this. Normally all ratings are mentioned, right? આના થોડા તમારે સેટ કરવા પડશે. આ સોર્સ ઇન્ડક્ટન્સ એ બધા મેં સેટ કરી દીધા છે. This is shunt active filter. 6 IGBT તમે યુઝ કરો. Nowadays we are using advanced power device. કઈ advanced power devices આવી ગઈ, યુઝમાં પણ આવી ગઈ. એને કહેવામાં આવે છે સિલિકોન કાર્બાઇડ, SiC યુઝ થાય છે, or GaN device, gallium nitride, બરાબર? SiC and GaN device and SiC MOSFETs, they are in use and it is used as this IGBT bridge, right? Okay. So next, over. Question, comment? Ravi sir.
બીજું છે ને પેલું એકી
હા 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 એચી
એ તો હજી બાકી છે એકી.
હા તો 2 મિનિટ બ્રેક લઈ લઈએ પછી ચાલુ કરીએ. on that q is equal to
ના વાંધો નહીં,
d1
તમે
by
આપણે
x
PPT લઈને
d1
તેનું તો આપણે
minus
સમય
d2
એટલે વાંધો નથી.
cosine of del 1 minus del 2,
હા
right? So it is dependent on power angle, and so suppose here there is a 1 at an angle 2 degree and there is a 1 at an angle 1.5 degree. This reactance is 1, right? So one's power is equal to 1 into 1 divided by 1 sine of 2 minus 1.5 degree. So one time it is a plus, and the moment this angle changes, instead of 1.5, this will become 2.5 degree, right? So this power becomes negative. So it's a huge reversal. तो ये जरा ध्यान में रखो. And in this case, as it is 2 degree or 1.5 or 2.5, not going to change, as cosine angle is not changed, right? Cosine of plus 0.5 degree or cosine of minus 0.5 degree, it is not going to change, right? So that's why it depends on active power. राहुल पढ़ी नहीं खबर
U voltage पर U voltage पर depend also.
हाँ.
Depending पर.
પણ કેમ એક્ટિવ પાવર પર નહીં? So that is the reason.
So it is remain same.
हाँ, because it contains cosine term, right? So it is either cosine of 0.5 degree or minus 0.5 degree. It is not going to change. બરાબર? એટલે see 0.5 degree થી minus 0.5 degree થાય, so there is a whole reversal. Active power નું sending end થી receiving end, receiving end થી sending end reversal થાય છે. Whereas if you take reactive power, તો reactive power માં કેવી રીતે change આવે? So if you take 1 here and 1.2 here, or if you take 1.2 here and 1 here, so you can see the change, because there is no change in this component. Only the change is V1 minus V2, right? Getting? This way you can judge. So here it is, say once it is 1, this is 1.2, right? So 1 upon 1, 1.2 minus 1 into whatever cosine, right? Next time what happens? Q is equal to 1 upon 1, 1 minus 1.2 into something. So this is voltage dependent, and that active power is angle dependent. And one more thing, have you heard about term K factor? हाँ, DKD. Transformer by incorporation of harmonics, transformer is derated. દાખલા તરીકે ટ્રાન્સફોર્મર 200 kVA નું હોય તો એમાં જો હાર્મોનિક્સ આવી જાય, બરાબર, નોર્મલી આવું થતું હોય, because transformer is everywhere, distribution transformer in bulk, બરાબર. તો this transformer is supplied through non-linear load, તો K factor term introduces, right? As K equal to 1, so that means there is no harmonics in a system. Transformer is supplied with a linear load, but K equal to some numbers are given, 4, 13, then harmonics are naturally bound to happen, right? So that is K factor, that is deterioration of transformer. So it depends on hysteresis and eddy current loss. Major factor is eddy current loss, because it is frequency square dependent, right? So it's K factor. So transformer is getting derated. Suppose the K factor is something 0.5, so transformer is operated at 200 kVA, so it may happen that it operated at 100 kVA. So at 100 kVA transformer becomes noisy and heating takes place, right? એટલે if you take particular transformer and if it is supplied by harmonics, so transformer is either 60% or 70% or 50% load પર જ operate થાય છે. If you need to change, if you want that my transformer should operate on its own capacity, so then what you have to do, you have to take from manufacturer K-rated transformer. K-rated transformer. So what does they do in K-rated transformer? K-rated transformer માં એમ્પિયર ના પેલા જે કંડક્ટર છે તે થોડા હેવી સાઇઝ કરેલા હોય, બુશિંગ ફર્નિશ કરેલા હોય અને મેક્સિમમ હાર્મોનિક્સ અવોઇડ કરવાની ટ્રાય કરેલી હોય, અંદર ઇનબિલ્ટ ફિલ્ટર આપેલા હોય. So such transformers are K-rated transformer. So if you use K-rated transformer, then you can operate on your own capacity. Like 200 kVA hoy transformer rating. So by K-rated transformer, you can operate on 200. બરાબર? તો આપણે ચાલુ કરીએ. મારી પાસે આનું બહુ ડિટેલ configuration નથી. Just I downloaded from Google and started, right? So automotive industry has been powered by internal combustion engine over a century. Industry is moving away traditional internal combustion engine, climate change, foreign oil dependence. So currently we are shifting to EV, but there is limitation with EV, right? One, there is a IC engine, other there is a EV. Okay. So EV offers a better performance and lower operating cost, where compared to traditional vehicles. One of the biggest issue is size and cost of requisite battery pack. So if you use EV, so there is a limitation, right? I have two vehicles. One is I started with EV. I took a two-wheeler. So that was a purely EV, but then I need to change. Sena par change kare Brezza, so that's a smart hybrid, right? So it's another technology. With an increasing car production every year, the fuel consumption increases, and hence the pollution increases due to emission from internal combustion engine. So one issue is pollution. Car needs a source of proposal which develops a maximum torque at zero with minimum pollution. The classic IC can't achieve this. Instead, electrical vehicles are used which reduces pollution to a greater extent. Vehicle which uses two power sources are called hybrid. So one is IC based, other is water based, electrical. This is overall limitation that battery pack, and that affects the overall vehicle energy consumption, right? So we prefer hybrid instead of direct EV or IC. Hybrid is preferable. HEV mitigates the cost and weight issue by the using smaller battery packs and downsize engines. Energy efficiency. You see, there is a IC engine and motor. So in both cases, torque and power at at particular RPM that increases. Like electric motor, if you take a case 3000 RPM, and here also if you take a case of 3000 RPM, then power and torque is almost 210 to 250, whereas it is going to change in electric motor. So torque and power requirement at low RPM, right, is high. 3000 RPM is enough, but power requirement and torque requirement is high. So normally EV is preferred. These are three types of battery electric, hybrid electric, and fuel cell electric. So energy sources uses in BEV is battery and ultra capacitor. HEV ma battery ultra capacitor is option and IC. There are two power sources. And in fuel cell, electric motor operates with fuel cell only. So there are certain advantages and problems, right? So we normally go for HEV. HEV is a combination of pure electric and pure IC based engine, right? So component of HEV is IC engine, electric motor, battery pack, its control system and transmission system. This is the architecture of HEV. Motor generator, battery, IC and control system, and that transmits power to wheel. So HEV basically of three types: series hybrid, parallel hybrid, and power flow. You can see here, this is a series hybrid model where wheel per power transmission, that is continuously by generator, battery and motor. Whereas in case of parallel hybrid, battery is separately connected, one is via engine and one is via motor. This is a good diagram. Series and parallel hybrid. So if you see here, in series HEV, functioning as a battery powered EV, where a generator driven engine supplies power to the battery or motor, which propels the wheel. Its main advantage is weight reduction due to absence of mechanical transmission. And large battery, engine and accessory increase the cost. Energy conversion inefficiency arises from mechanical to electrical and power. In parallel HEV, both the engine and motor can drive the vehicle, whereas the EMS selecting, that is energy management system, it's one of the issue where you can work. Motor typically propels the vehicle at low speed, increasing the fuel economy. And third one is a power split HEV, combines series and parallel architecture of a greater efficiency. This is hybrid vehicle. આના વિશે થોડું ડિટેલમાં લખ્યું છે. You can go through and it will be useful. There are different energy modes, બરાબર? So that modes are explained. Main thing is in HEV we are using Why not induction? Hybrid electric vehicle, if you see, we are going for PM, permanent magnet synchronous motor. Not induction, not BLDC. Of course, BLDC is used at low level application, right? Direct torque control is not available, right? In case of BLDC. So if you go for a low range like two-wheeler, so there you can use BLDC. But if you go for a motor or car, the PMSM is preferred, right? And why not induction? If we are using already PMSM, then we can use induction motor also.
Induction motor power and torque, they will be.
No, almost similar. Power and torque induction motor 3-phase is almost similar of PMSM. But the additional rotor copper loss that restricts the application of induction motor in case of PMSM. So PMSM is preferable because rotor is eliminated, right? So PMSM use high energy magnets such as rare earth. PMSM drive is designed for high power density, high speed and high operation efficiency. These advantages are attractive for their application is EVs and HEVs. So these are some comparisons are presented in case of PMSM and BLDC. Brushless AC synchronous motor, this is brushless DC motor. Torque ripples are absent, torque ripples are present in case of BLDC. Performance efficiency is high, performance efficiency is low. More efficient, less efficient. Used in industrial application like automobile, servo, robotics, train drive, and here it is. Train drive, locomotive, electrical my use type, right? Produces low noise and produces high noise. BLDC and PMSM are almost compatible, right? But direct torque control facility is not available, so we are using in two-wheeler application only. BLDC is now restricted to two-wheeler. If you go for a four-wheeler, there is a PMSM drive. बराबर? एना एडवांटेज थोड़ा डिस्कस करिए सर. Same. So this is PMSM motor, right? Here it is shown induction. There is a rotor bar, so that creates an additional rotor loss. बराबर? It can be eliminated in case of PMSM, as it is permanent magnet, right? So there is a limitation of induction motor, and we are using PMSM. These are the reasons. अच्छा, EMF and torque equation. It is same as DC. If you see, जो this is EMF equation. It is as good as DC. Flux, frequency, TPH, number of turns collected in series per phase, and KD and KP, distribution factor and pitch factor. So it is as good as DC. The torque equation of synchronous motor is given as this. Power equal to torque into omega. Torque equal to power into omega. એટલે omega, this is power. Power equal to torque into omega. So omega comes in denominator, and that is a torque. Torque developed is equal to power divided by omega. આ એક મોડેલ છે. You can use EMS also. EMS is energy management system. So that is one area where you can poke your nose. If you want to do some research, so energy management or a battery management in case of hybrid electrical vehicle. area. So this is MPG is 1 ton used, distance travel per energy consumed into energy content of gasoline, right? So this is balance between ICE traditional fully electric and hybrid vehicle, right? So it shows that hybrid vehicle at some extent it wins. There is a limitation of pure EV, there is a limitation of ICE. This is EMS. So one can go in this area, deep learning based EMS, right? Rule based, optimization based, reinforcement based, and deep learning. So if you want to pick up a topic, then EMS, deep learning based energy management system in HEV. This one of the probable and competitive area right now. And a control aspect, if you see PMSM, there is a series and parallel number of batteries are used, and 400-volt pack of a battery is prepared, right? So that drives the PMSM directly by field oriented control or vector control, or a scalar is not used, right? As per other accessory, if you need to convert 400 to 48 volt or 24 volt, like wheel driving and other accessories, so that is internal facilities available. There they are using DC-DC isolated buck boost converter. So basically there are two drive. 400 volt is directly fed to PMSM, and 400 volt to DC-DC converter, either 48 volt or 24 volt, to operate the other accessories of the motor, right? So this is the basically system used in PMSM drive. 400 volt directly will be fed and it will be converted into DQ, DQ to again alpha beta, and then space vector modulation, and again given to three-phase system, right? This is also one of the area where you can involve and this is the final control technique. You can start directly working on it, right? It is a very good area where again here they are using SIC, MOSFET or IGBT or a GAN device, 6-pack, right? This is DC link capacitor and high frequency current. This is main aspect of this EMSM control. Okay, how it is being transferred from alpha beta axis to DQ axis, right? So Q axis generally represent reacting power, right? So Q set to 0 in DQ, so it is eliminated, and on direct axis you can have a torque operation, right? And this is a courtesy by Texas Instrument DC-DC buck boost isolated converter use, 4 switches, coupling inductor and block diagram. That's all. एक ऑपरेशन समझावવાની ટ્રાય કરીએ DC બસમાંથી આ સ્વિચ ઓન કરીએ Q1 ને Q3 તો બેટરી ચાર્જ થાય છે અને પછી બેટરી રિવર્સમાં ચાર્જ થાય. So you can have a buck boost operation simultaneously. That's all.
Second way is you consider your system dynamics in continuous form and your measurement in discrete form. So That's why it is called continuous discrete dynamics. Continuous discrete dynamical system, and that's why it is called the hybrid estimator. So we consider here extended Kalman filter as a continuous discrete extended Kalman filter. So your measurement is discrete, whereas your system dynamics is continuous. Okay. So in this way you correlate these things and write your outcome of the paper, new research direction of the paper, new ideas of the research paper. In this way you have to discuss with your team and note down in sheet given by us.